Hey everyone. Today I had the pleasure of speaking with my former roommate and good friend, Dr. Soud Al-Kharusi. He is a postdoctoral researcher at Stanford University and recently graduated doctoral student from McGill University. His primary research focuses on astrophysics and seeks to answer questions such as: is there a connection between the fundamental forces, gravity, electromagnetism, strong and weak? What is the true nature of space and time? Are there extraspatial dimensions? How can we detect the neutrinos that were released around 1 second after the Big Bang, or those from supernovae? In this episode, we discuss some of the fine work written in his Ph.D. thesis, on top of general physics questions about how time and gravity work, how can we observe quantum mechanics, etc. This was my first time recording a physics episode, so I was genuinely nervous at how ignorant I really was at my knowledge of physics, and I was worried about how I would perform. However, I think it turned out just fine, and Soud and I are in the talks of a second episode sometime down the line. And now, with that said, here's my conversation with Dr. Soud Al-Kharusi. So, soon to be Dr. Al-Kharusi, thank you for taking the time to come on my podcast. I really appreciate it. Also, thank you for being a sick roommate. It's nice
Yeah,
to...
no, of course. Thank you for inviting me. I think this is going to be a fun experience for the both of us.
I too, as well, because I'm an arts guy and I like to be
Yeah.
more knowledgeable, and I think you're going to school me on a lot of things.
Well, we'll see. I mean, I think it's fun to have a discussion about whatever people are passionate about. So
Yeah.
we'll see.
I also like to complement physics with art. I think that's very cool. So before we get into the nitty-gritty of what you do and what you studied, I was wondering if you could give a brief background about yourself, just so people kind of get accustomed to who you are.
Yeah, sure. I mean, so I'm Soud Al-Kharusi. I was born and raised in Oman, spent 18 years there, moved to Canada for my undergraduate degree in physics at McGill. I finished that in 2018 and have since been doing a PhD in physics, also at McGill, and I am wrapping up hopefully in a couple of weeks.
By wrapping up, you mean like defending your thesis?
I'm defending my thesis in a couple of weeks, and so this is it's a pre-defense.
It's a pre-defense
It's
talk.
a pre-defense talk.
But we're not going to talk about just your dissertation, because it's awfully technical. I could only go through about 3 pages before I had to give up.
Yeah.
But can you actually tell us what your dissertation was on about?
Sure, yeah. So what I was working on for the last few years is an experiment called the nEXO experiment, which is a radioactive decay experiment looking for a decay that doesn't actually exist. We haven't seen it yet. It's hypothetical. But if we do see indications of this decay, then we learn stuff about neutrinos, which are these fundamental particles that are all over us and passing through us at any given moment.
Okay.
Yeah.
Let's start with first things first. What is a decay in this instance?
Sure. I mean, so you have a nucleus that starts off in some state. So in the same way that you have transitions between different states in atomic spectra. So if I have a fluorescent tube and it's emitting light, you're applying some energy, you're exciting those atoms, and that's a chemical process where the electrons are jumping between different energy levels. And the emission of that or the absorption of that is a transition between two different states. For nuclei, similar things happen, but you have transitions between protons and neutrons, and it's much higher energies that are being emitted. In this case, in the case where I'm thinking about, it's called double beta decay, where the nucleus converts 2 neutrons to 2 protons and emits 2 electrons all simultaneously. Those electrons have MeV scale energy, so like mega electron volts, but that's a detail you can skip over.
Okay.
And we just measure those electrons coming off because they're charged particles, and charged particles like to interact with matter.
Okay. And what are neutrinos?
So neutrinos are sort of like these very light, like less massive versions of electrons that don't have an electric charge. And that makes them really interesting to study because, for one, they're hard to detect, and 2, they are also the only particle in the standard model, which is the table that collects all the fundamental particles that we know of so far, that only interact via the weak force.
Okay. And how unique are neutrinos? Because in your dissertation you say they're fundamental, but they're also very hard to study.
Yes. So in the sense, they're unique in the sense that everything else in the standard model that makes up matter, so all the fermions in the standard model are charged particles. So the techniques you use to detect them, like basically when a charged particle exists and it moves through a magnetic field, it bends. When it goes through something that it can be ionized, it ionizes. So that's why we talk about ionizing radiation a lot. And you can measure the effects of this ionization process.
Can you give an example?
Yeah, so for us, we're using liquid xenon as a medium. So xenon, the noble gas, we condense it into
Isn't
a
that
liquid.
54 on the periodic element?
Yes, it is element 54. And we have a bunch of liquid xenon, and essentially any charged particle that passes through the xenon ionizes it and causes it to glow, and it glow in a very specific way. And that's called scintillation light, and we measure that scintillation light as well as the kind of ionization track that's left behind. And combining those two things, you can reconstruct what type of nuclear decay happened.
Okay, so it sounds like you're studying particle physics, given how in depth you are with the specific particles right now.
Yeah, so it's pretty much the thesis. My focus has been, I would say, particle astrophysics. It's been a mix of like 3 different fields. For example, this double beta decay process is a nuclear physics process, but we're exploring it to do particle physics experiments, so measurements that tell us about the particles themselves, in this case, neutrinos.
Okay. And can you give some people an idea of what your work actually consists of? Are you working in a lab that's like using lasers or whatever other techniques that I don't know of?
Yeah.
Or are you working computationally? Like what does your work look like actually?
So most of my work has been computational, but we also have a lab. I worked in the lab for a couple of years, but then have since had to narrow the scope of what I'm doing just to finish the Ph.D. on time. But yeah, we have a lab. This is an experimental project. We're designing an experiment. And what I've been doing in my thesis anyway has been basically doing computational physics simulations of various processes in order to better design the experiment.
Okay.
And optimize for what we're trying to look for. Yeah.
What's the advantage with doing physics computationally?
Well, it's not necessarily an advantage. It's just there are rules in physics, right? So we know we can predict what would happen when a charged particle passes through various media. And once you embed that in some sort of simulation framework, you can build all sorts of detectors from your imagination and just simulate what they would look like for various processes. So what your end result would be. And that way, you don't have to build 100 different experiments to do the same thing. You can simulate a bunch of them, optimize them for what you're actually trying to measure, and then just pick one and actually construct it.
Okay. And how new or how robust is computational physics compared to, let's say, last century?
Well, computational, it's a very broad term. So I'm specifically talking about like particle physics Monte Carlo, which is like a very small subset of the realm of computational physics. Because, there's computational physics. I'm not the right person to ask in terms of like people do material science and solve like basically Schrodinger equations, I think. I don't even know. And that's a many-body like quantum mechanics problem, and that's a very different simulation technique than what we do, which is essentially throwing random numbers, because the way we treat particles interacting is they have a probability of interaction every time they approach another particle with some given distance.
Okay.
Yeah.
And there's something that you mentioned earlier, which was charged particles.
Yeah.
Is it possible for a particle to not be charged?
Yeah, so neutrinos are uncharged.
Oh.
So as soon as they're born, they basically travel in a straight line, for as far as we can tell, forever, until they interact with another particle and somehow emit some charged particle in some process.
Okay.
And so what we actually can measure is the result of that.
Oh.
So we measure the charged particle that's emitted in the end, which you can either think of as the neutrino being converted into the other particle or as another particle being emitted.
Okay. And it is established that neutrinos go beyond the standard model. And I was wondering if you could... Yeah, go ahead.
Yeah, so it's not that neutrinos go beyond the standard model. It's that the fact that they have masses, it's not obvious how to account for that in the standard model.
Can you explain further?
Sure. So the way we think fundamental particles have their masses come about is through what's called the Higgs mechanism. And the Higgs mechanism, in short, is a way to kind of marry the left-handed and right-handed components of various fields.
Okay.
And when you do that, you actually intrinsically gain a mass for that particle based on how strongly it couples to the Higgs field. So it's like a three interaction term where you have the Higgs and you have the right and left components of the fields, and they're all glued together. The neutrinos, only the left-handed components can interact with the weak force. The weak force completely breaks this left-right symmetry.
Okay.
And so you either have to admit a right-handed neutrino field, which we know we will not measure, at least through the weak force, and since it doesn't have an electric charge or doesn't interact with the strong force, there's nothing we can do to measure them. So you have to just hypothesize that these exist and then marry them to the left-handed components, and then you can get a mass this way. Or you have to think of some other mechanism to generate the neutrino masses.
Okay. And how important is symmetry in physics? And why is it important that neutrinos they're not anti-symmetric, but they don't work exactly with these symmetrical laws?
So, I mean, symmetries in physics, it's very important. They're very important. But what you're asking about is neutrinos right now?
Yeah.
So could you repeat that question? Because I got sidetracked there
That's
for
okay.
a second.
So obviously symmetry is extremely fundamental to physics, and you're saying neutrinos do not interact symmetrically, correct?
Yeah, but the types of symmetries we're thinking of are different, I think.
Okay.
So this kind of left-right handedness symmetry is a discrete, it's kind of like a reflection in a mirror. But there are more, there are many continuous symmetries that are associated with conservation laws through this thing called know this theorem, which is
Know this theorem?
no, I wish it was know this theorem. Know theirs. So it's
Okay.
Know there. She was a mathematician back in the early 1900s. Wrote down this theorem that essentially shows that for symmetries of this mathematical object you can construct called the action of any physical system you can think about, any symmetries associated with the action have to be correspondingly associated with some conservation rule.
Okay.
So in that sense, symmetries are very important in physics, because if you notice a symmetry in your action, then you know that there has to be some mathematical object that is conserved throughout the processes that will occur in that system. Does that make sense?
Yeah, it does make sense. So what don't we actually understand about neutrinos then?
We don't understand how they have their masses. We know that they have masses, and we don't know what mechanism by which they generate them.
Okay. And what is a
That's-
mass in this instance, actually?
Mass is kind of your resistance to motion in a sense. So this is like, the way I'm thinking about it is inertial mass, but there's also gravitational mass. And, if you have this property, that's, if it's large enough, you end up bending, your space-time. But that's not neutrinos. Neutrinos are extremely light, and also all these fundamental particles are extremely light that you can basically treat the space in which they're operating in as completely flat.
Right, like of the atoms themselves.
Yeah.
Yeah.
So mass in this sense is just like it's a tool that we can use to be able to show how the dynamics of a system will evolve.
Okay.
From an inertial perspective. So something heavy will continue moving in a straight line if it's very heavy compared to a light thing that knocks it, for example.
Right.
Yeah.
So what you're saying is that what we don't know is how they get their masses, essentially.
Yeah.
And what's the hypothesis around as to why they might have their masses?
So I can tell you how we know they have masses.
Yeah.
Okay, I will draw this on this piece of paper, but eventually
we will digitize it afterwards.
We'll digitize it afterwards. But you basically have a situation where each neutrino is associated with another particle, okay, which is called a lepton. So an electron is the lightest one of these. An electron is charged, and so is the muon and the tau particle. And there are 3 neutrinos, one associated with each of them.
Okay.
When you have a particle physics process that occurs, so some interaction occurs, and you convert in some sense between these two states, between the neutrino state and the charged particle state, for example, you create neutrinos in what's called a flavor eigenbasis. So in one of the flavor eigenbases. And what that means is like these are three different flavors here, 1, 2, and 3. And when a neutrino is born, it's born as one of them. Okay?
What do you mean by born?
When a neutrino just pops into existence from some other physical process.
Do we know how that process occurs or no?
Yeah, there are many processes that can emit neutrinos.
Okay.
So like in the same way that like you can have something hot emits like photons, like it glows red.
Or like these lights, I guess?
Or these lights, yeah. This is like a chemical process emitting photons. Yeah, so that's, that's an electromagnetic process.
Right.
So weak interaction processes can emit neutrinos.
Okay. And what are examples of weak processes? Forgot the middle word.
So, well, that's just anything that is mediated by those bosons you have on the table over there, which is a funny term to call them, but essentially they're these other particles called the W and Z bosons, and there's 3 of them. There's a charged W, so it has a positive and negative charge, and then you have the Z boson, which is like a neutral particle. These things are heavy, and when you construct like an interaction, but you still have to obey all the rest of the symmetries of the standard model, there are certain processes that are allowed to occur. So the case I'm thinking about is like when you convert between a neutron to a proton in your nucleus, like going back to our beta decay example. If you convert between a neutron to a proton, you have to conserve charge, so you have to also emit an electron. Because protons and electrons have opposite charges, and this has a charge of 0, the neutron has a charge of 0, and that's cool. Now, but you also have to conserve something else called lepton number, which is associated with these neutrinos. Because an electron is part of this lepton family, so you can't just have it show up out of existence, out of nowhere. So you also have to emit an anti-electron neutrino. So this is how an example of how a neutrino
Which is like
born.
antimatter, right?
Which is a version of antimatter, yeah.
Okay.
And this is an example of how a neutrino can be born. So now that it's born in this flavor state, this electron type. But as it moves through space and flying through space, you can detect it sometime later by the reverse of this process, for example. And when you do that, you either emit a muon, a tau, or an electron with some probability.
Some probability.
Some probability, which we can calculate.
Is it random, or is there a specific number to it that's like consistently reoccurring?
It's random in like, it's consistently reoccurring as a function of energy and distance traveled. Okay. But it's not random in the sense that it's just some random probability. It's like, okay, the chances of it being an electron is 1/3 at this distance and this energy. But if you move slightly further, the chances of it being an electron is like 1/4. So the whole total probability sums to 1, or at least we hope so.
Okay.
Unless there are other types of neutrinos that we're unaware of.
Okay. So then if we understand how they gain their masses, what does that exactly reveal to us about, I guess, particle physics / astrophysics, since this is happening in space, correct?
Yeah, this is happening everywhere.
Everywhere, okay.
Yeah, it's not really revealing to us that, well, one thing that's interesting is if we do know how they generate their masses, for example, the experiment we're trying to look for this thing called neutrinoless double beta decay. So if you have this exact process, this neutron to proton conversion, and instead I have 2 neutrons converting to 2 protons plus 2 electrons, and I don't emit neutrinos, right?
Right.
For some reason, you can imagine that these 2 neutrinos are antiparticles of each other, and they annihilate within the nucleus. This is one way to imagine this occurring. If this happens, then you know that lepton number, which is one of those conservation rules, is not conserved.
Okay.
So suddenly you're in a situation where you've created more leptons than anti-leptons from a physical process. And so now you can imagine how this relates to like the whole like matter-antimatter symmetry problem. It's a much deeper hole to actually get there.
Right.
It's not as simple as, the matter-antimatter problem is not solved by saying these decays occur in the early universe. That's not what's happening.
Okay.
But this allows other physical processes to occur that do not conserve lepton number as well. It means it's possible. And the reason that's interesting is because there's no symmetry that's actually imposed on the standard model that tells us that lepton number needs to be conserved. It seems to be conserved as far as we can tell. So in that sense, that's why it's very interesting to me. It's like this is an accidental symmetry is what people call it.
Okay.
It's that it's not coming from some underlying kind of there's no underlying system. Yeah, there's no underlying symmetry of your system that tells you that lepton number is a conserved variable across physical processes. It just so happens so far.
Okay, and how common are these, I guess, dead ends in physics in general? If it's appropriate to call it a dead end.
What do you mean by dead end?
Well, as in you said there's no real formula to really establish this loss of conservation.
As far as I know, there isn't like a symmetry that leads to lepton number conservation.
Right.
Which is why I think it's interesting to test.
Okay.
Because, you don't have to know that certain symmetries give you conservation laws, but you know that if you have conservation laws, then you have to have some symmetry. You don't have to have, well, actually you might have to have one. But anyways, my point is we don't know what the symmetry is, so we don't end up with the conservation rule associated with it. We just seem to observe the conservation rule. And that's part of what physics is, right? A lot of it is just observing the world and seeing how it works and then saying, okay, this is how the world works. Can we explain why it works this way?
And when you say the world, do you mean on Earth or in space, or both?
Both. I mean, from the perspective that I'm talking about the world, I'm assuming that the physics is the same across the universe.
Right.
That's not necessarily something that everyone agrees with, but there's very few arguments for why it wouldn't be the same across the universe, and they're pretty on the fringes of physics today, I think. But I think it was Dirac who did actually postulate that maybe physics does change over time. For example, the fundamental constants of nature are not fixed, versus in the framework that I'm explaining to you right now, like the electron's charge, for example, is the same now and it will be the same in the future, and it has been the same in the past.
Okay.
Yeah.
Can you go more on this lack of fundamental change in nature, or the reverse, excuse me?
What do you mean?
Like the theory you just postulated.
Well, it's not, I don't really know much about it.
All
I know is that Dirac has postulated this, and there are papers written about this, and as far as I'm concerned, if there are ways to test this, then it's interesting, and if it's not testable, then it's not really physics.
That's
if
fair.
you're just playing around with mathematical models, it's like, that's cool, but that's mathematics.
Yeah, I would agree with that.
Yeah.
You also mentioned earlier that there was an antimatter and matter symmetry problem. Could you go more into that?
Yeah, so for every particle we have in the standard model, so that includes electrons, protons, neutrons, protons, neutrons aren't a part of this, the quarks that are making up protons and neutrons, plus electrons, muons, and tau particles, these things I just drew over here. You have an antimatter version where you take all the quantum numbers and you flip them, and you end up with the same particle, same mass, everything's the same except all the charges are flipped. The scenario we can think of most obviously is electric charge. So you have an electron, you flip its charge, you end up with a positron, which is an anti-electron. Okay, and these exist, and that's how PET scans work, actually. We measure positrons annihilating with electrons in cancer. And when you do that, you can reconstruct where that annihilation happens, and that's how you detect where cancers are. Anyway, so this is a real thing. What I will say is that the world we live in today, if you look around, the vast majority of all particles we have around are made up of regular matter. Like 1 in 10 to the 9, I think. So which is 1 in a billion particles that are just kind of in existence are antimatter particles. And we don't know why this is the case. We don't know why there's such a huge bias on one side of this. When physical processes, as far as we can tell, tend to conserve either the number of matter particles or the number of antimatter particles in any system. That's the matter-antimatter symmetry problem in short.
And what are the proposed, if you know, obviously, what are the proposed solutions to this problem as you
there are many proposed solutions. I mean, now you're getting into the realm of like cosmology, which is the study of like the universe as a whole, and the history of the universe. And Sakharov in like the 60s, I think, proposed 3 axioms that basically said, for you to dynamically create an asymmetry between matter and antimatter, you have 3 conditions that need to be met. First, you need to not conserve baryon number, which is the number of baryons, and these are a class of particles. So that has to not be an actual valid conservation rule. The second is that the system you're in needs to be in a non-equilibrium state. So you can't have like a thermal bath where it's just everything is just stable. You have to have some non-equilibrium state. And the third is that you have this combination of discrete symmetries, which is charge and parity. So that parity is this mirror reflection thing, the right and left-handedness. Charge is like electric charge, for example. And the combination of the two needs to not be conserved as well in some processes. So if you have all these 3 conditions met, there's a way to generate an antimatter-matter like asymmetry between the two. Now, that's not necessarily saying that that's the solution, because there's no mechanism to do this right now. Or there's no mechanism that's kind of at the forefront. But one way is people talk about is called leptogenesis, which is kind of related to this double beta decay process in some sense, which is if you have a situation to generate neutrino masses that doesn't require there to be these kind of right-handed neutrino fields, and you can actually, you have the right-handed neutrino fields, but there's something that allows you to couple only the left-handed fields to each other or only the right-handed fields to each other. Then, if these things are really heavy, and they existed in the early universe when things were very hot, and like when things are very hot, energies are high. When energies are high, you can generate more massive things. But then the universe is expanding rapidly. And as the universe expands, it cools. And at some point, the kind of forward and backward process of creating these heavy particles, you kind of only allow them to decay. But because you can't generate them anymore because the temperature has dropped enough. And if you allow them to decay using some fancy like selection rules in like particle physics and kind of obeying the symmetries of the standard model, you can sort of maybe see a pathway for how this happens. Anyways, like this is a very brief summary, but like the mechanism that I'm referring to is called leptogenesis, or the class of mechanisms I'm referring to are called leptogenesis.
Or section 2.3.2 in your thesis as well.
Yes. Yeah, I tried to briefly go over it there because I think that's an interesting connection between like, essentially what we're doing is we're just looking for a hypothetical form of decay, but it's actually connected in a very real sense to if we see this decay, then there's a pathway to explain the matter-antimatter problem, which is a cosmology problem, using this nuclear decay, which we're actually doing to try to understand something about this particle called the neutrino. So like the way physics is connected between different domains in some sense is super interesting to me, and I think it's worth like highlighting.
I agree. So I have 2 like follow-up questions. The first one being, are there anti-neutrinos, and do they behave in exactly the converse or reverse of neutrinos?
There are anti-neutrinos in the sense that like when they interact, when we see some neutrinos interact, they produce antimatter particles instead of regular matter. So this thing that's emitted over here in this double beta decay process is an anti-neutrino because it comes out at the same time as a regular electron. So you have to kind of cancel out the matter-antimatter in this situation, right? Whether they interact exactly the same as regular neutrinos, we don't know, and that's actually part of the ongoing like big global neutrino physics program is trying to understand this. So these are the general class of experiments are called like neutrino oscillation experiments, and the big ones that I can think of that are coming online or are online are like Dune, Hyper-K, and the Juno experiment are the 3 like next gen.
And where are these being done?
So Dune is going to be based in the US at Fermilab, which is I think near Chicago.
Okay.
Hyper-K is in Japan, near Kamioka. and Juno is somewhere in China, in Jinping, I think. And yeah, they're all pretty much using different experimental techniques to try to see if regular neutrinos and antineutrinos oscillate in different ways, or they oscillate in exactly the same way.
And do you know the results right now, or is it still like a huge...
No, this is an open question. So this
Yeah,
is like
okay.
people are working on building these experiments. Yeah.
And you also mentioned that neutrinos play a significant role in the early universe, as did heat. What is their role exactly?
Well, in the sense of, so neutrinos are super duper light, like I
Right.
said, right? So the energy kind of barrier you need to create them is quite small. The other thing is neutrinos don't have an electric charge, so the way they interact with like other stuff in the early universe is different than things that are charged, number one. And number two is that as the universe cools, you go from particles behaving in a relativistic manner because they're super, when things are really hot, things have high energy. If that energy is about the same order of their mass through this like E equals mc squared, then you would say the particle is relativistic, which means the kind of mechanics that it undergoes is like, you don't treat it as a classical physics problem anymore.
Is that why it's beyond the standard model?
No, that's all within the standard model.
Oh,
That's,
okay.
that's not
Okay.
anything fancy. That's like special relativity, like,
Okay.
yeah, Einstein, 1905.
Okay.
um,
Oh, it's over 100 years ago.
yeah, it is over. It's crazy. But what neutrinos do in the early universe is essentially like, as the universe cools, most particles become non-relativistic at some point, and neutrinos stay relativistic for a bit longer. So now you have this soup of photons, like regular light, and neutrinos, and there's so many of them, and the neutrinos do have mass, as we know, so they actually start to smear out to the clumping of matter. And depending on how quickly the universe's temperature drops, the mass of the neutrino, et cetera, you can sort of try to imagine like the universe is trying to clump together, but you have these neutrinos that are massive that are kind of smearing that out. So instead of having larger clumps, you kind of...
They space
Small.
out, I guess?
Yeah, they space out. So I believe, this is not my area of expertise, so like everything I say with a grain of salt, but I think you start smearing out like small scale structure formation, so like smaller clumps rather than larger ones, depending on how many neutrinos you have and also the energies at which they're moving relative to the universe's expansion, something like that.
And do they keep their energy levels kind of the same when everything cools off because they're so light?
No, they actually get, so when we observe them, like you have things in the universe are rapidly moving away from us, right? The further and further you look.
Well, aren't we moving as well?
Yes, but like the distance like between us is actually quite close on a cosmic scale. So we don't actually notice this. But and also there are other forces that are keeping us together. Like the Earth is a massive gravitational body that's attracting us. But when you look at cosmic distances and you try to see, well, you can see this with light. When you look at things further away, they get redshifted.
Yeah.
So it looks like the light is getting Doppler shifted as if something is pulling it away. This is not actually what's happening, but you can imagine this as like when you have a car coming towards you and it's honking its horn, it goes meow, and then it like drops in frequency as it passes you and it starts moving away from you. And that's a Doppler shift.
Okay.
But the horn is not actually changing its physical frequency. It's just the way the waves are hitting your ear that are coming in rapidly as the car is moving towards you, and then as it moves away, they're coming in more slowly because the car is carrying away some of that velocity. This is not what happens with light, but you can think of it in the same way.
Okay, that was a very good analogy, by the way.
Yeah, so as things are further away, they seem to be moving away from us even faster, so things get redshifted even more, and you can measure that. So the neutrinos from the Big Bang, in this sense, are actually very low energy if we ever see them, but they're predicted to be very low energy today. And actually the only source of non-relativistic neutrinos, as far as we can guess in today's world, would be neutrinos from the Big Bang, and there are experiments actually trying to search for those neutrinos themselves.
Are they in the three places that you mentioned, or are they elsewhere?
This is a different experiment called Ptolemy, and it's not even, I don't think it's even under construction.
Oh, okay, so it's brand new.
This is brand new. This is a proposal. I'm not sure. Maybe I'm wrong. Again, like I'm also,
It's okay.
I'm only human. I make mistakes, so please take everything I say.
This is in your dissertation defense,
Yeah.
Okay, so we've been toying around with this word energy for a little bit. I was wondering if you could explain what that is, because it's to someone who doesn't really study physics, it might be a very empty term.
Yeah, so energy, I think like at the high school level, we talk about it as the ability to do work.
Okay.
So if something has a lot of energy, you can channel that one way or another to do something. And that's kind of where the story ends at like the high school level.
Which isn't very much, actually.
Which isn't very much, yeah. And it's kind of, I think it lacks the exciting, like beautiful part of it, which is, it goes back to this theorem by Emmy Noether. So when you write down this thing in this mathematical equation for some system called the action, and then I talked about symmetries of the action leading to conservation rules. The symmetry that leads to the energy conservation rule is a time invariance. So it's the fact, like the way it's popularly said is like, if you do a physics experiment now, or you do it in 5 minutes or in 2 hours, the physics is the same. The result is the same. And that necessarily means that there's some quantity that is conserved throughout the process. That quantity is what we call energy. So there's a deep relation between time invariance and energy conservation.
Time invariance?
Yeah.
Okay.
As in things don't change if you do them now or later or in the past.
In a physics standpoint.
Yeah, like I can drop this pen now and I can drop it later in the same position and the same thing will happen. In a kind of ideal world. Of course, there are air currents and things that complicate this, but yeah.
Okay. And another thing that is studied a lot in physics and is gravity. And I was wondering if you could kind of demystify what gravity is in I guess a cosmological sense.
In a cosmological sense, I could say, okay, I can give two kind of descriptions that I think are interesting. One is Newtonian gravity, which is you have this something that's called a force that depends on two masses at some distance. So you have a mass, and this is like the charge of the gravitational force. And the higher the mass, the higher the force between these two objects. That was the Newtonian way of looking at gravity. And it falls off as like 1 over r squared. The way that we look at gravity now is that we imagine this geometric thing called space-time, and everything is essentially just moving on straight lines, or what are called geodesics. So they're just moving in straight lines all the time. And gravity is sort of like an apparent force because they're moving on straight lines on the space-time, but the space-time itself is bent. So when you bend it enough and you push something in a straight line, it just looks like it's being curved around. So we see it as a force, but really it's not a true force in the same way that like in particle physics we talk about forces. And we see it as like a manifestation of some geometric structure in space-time. And I think that's a cool way of looking at it, but it's also very different and a very different framework from the way we think about a lot of other things in physics.
Right, and this is actually something that I've been wondering forever. So if you go on Google Images and you Google black holes and their density, and you see this you see Earth and you see this concave shape around, and then you see black holes kind of go down.
Sure, I know.
You say kind of.
No, I know what you're talking about. Yeah.
What is this, how can someone actually kind of visualize this kind of depth thing. If like space is it's kind of like being in the ocean, like these 360 degrees that you can go everywhere, right, in all directions.
Yeah.
But how can it be like this flat plane necessarily?
It's not. So that's the thing. That's a visual aid.
Representation.
Yeah, but it's not actually bending in 2D like that. That's just the only way we can draw something bending in 2D is that way. But really, the thing that's bending is not even 3D. It's the 4D space-time itself. It's the
Right.
whole 4D object. So you don't actually, at least as far as I know, it's including the time is, because you have some coupling between time and space. But it's hard to draw that. It's really that's the answer I can give you. It's just like the picture you have in your head is like a lower dimensional representation of what you think is happening. Yeah, it's literally, yeah.
Okay, and what is the relationship between time and space? How is time actually a physical dimension?
That is a good question. What is the relationship between time and space? Well, okay, it's a dimension that has an interesting property, right? So like, we have three physical dimensions. I can move forward, backwards, I can move left and right, and I can move up and down.
XYZ.
X, Y, Z. And those are like degrees of freedom I have. But I can only move forward in time.
Right.
I cannot move backwards in time.
Is that the famous term, the arrow in time, that people sometimes use?
It's related to that. Yeah, I mean, the arrow of time, it's something people talk about a lot, and people really wonder about this stuff.
Okay.
We don't know, we don't have a solid answer, I think, as to why the arrow of time is only forward, for example. But when you imagine it from our like human brains, it's like, can you even imagine a world where it wasn't only forward?
No.
So then now we leave this realm of physics and we start wondering, like, even if it was the case that you could move forward and backwards, and we couldn't just computationally comprehend this in our heads, you end up with a world that can only move forwards in time according to our perspective.
Right.
So this is like beyond physics, but it's an interesting question.
What makes you say that's beyond physics?
Well, in the sense that what we're talking about is like untestable, right? So how do you test how our perception changes the kind of way we view the universe? Is the universe happening and we're perceiving it, or is it kind of we're trying to make sense of what's coming in via our senses? And our senses are, in this sense, like also expanded by experiments and detectors. Like those are just expansions of our senses, really.
Right.
So how can we imagine something that has nothing to do with our senses?
That's a good question. Not even the psychologists have an answer for that.
Yeah, I don't think it's it's not a physics question. It's just like a kind of philosophical, like, is the world out there actually this way, or is it because we can only allow ourselves to be, we can only perceive things in a particular way that we see it that way?
So just to clarify, you're saying that the relationship between time and space is a philosophy question, or just...
No, I don't know how to answer that question. I actually don't know how to answer that question well. I guess I would say that.
Does anyone have a good answer? Or
I'm sure people have good answers. There are a lot of smart people in the world. Yeah.
Right.
Yeah.
Okay. And speaking of dimensions, this is a conversation we've had in our household many times, but I would like to actually digitize it. First of all, what is a dimension? How many dimensions are there? And how do we know that we're in 3 dimensions precisely?
Sure. So, okay, what is a dimension? So a dimension you can think of as like kind of an axis where you are free to move along, right? So when we talk about X, Y, Z, X is a dimension where you can define as forward, backwards, for example.
Right.
Y this way, Z up and down. Those are the 3 spatial dimensions. There are 3 spatial dimensions as far as we know. Well, yes, there are, because we experience our lives in 3D. But people do talk about like extra dimensions being out there, extra spatial dimensions. Of course, they can't be too large, because if they were large, then weird things would happen. Like things could just disappear. Like you can imagine a situation where, like, if I lived in a 2D world, but there was if we were in 2D and I did this,
Yeah.
the pen from your perspective is just completely gone. It just disappears. But because we're in 3D, you know that there's something behind.
You might want to turn it for the camera, actually.
Sure.
Yeah,
Okay. I take the pen, I move it this way.
it disappears.
It disappears. But you know in your head, because there's a third dimension, that it's actually just behind us.
Right.
So in sort of subatomic physics, you can do the same, play the same game. You have a particle, does it disappear? Is there energy missing from some interaction? And that energy you can think of on a very high level as like leaking into these extra dimensions. So as far as we know right now, this doesn't happen. We search for extra dimensions and we don't see them. But that doesn't necessarily mean that there aren't any. It just means that they are not large, in the sense that as far, like X, Y, Z, we can move a lot in each direction, right? But maybe there is an extra spatial dimension that's just so tightly curled up that things that are larger than that size can't actually enter them. So you can imagine like taking a piece of paper. This is large, but now I roll it up really, really tightly. And now my coffee cup doesn't really experience this dimension anymore. It can't like be inside it.
But what you're saying is that it won't interact with that curled up dimension. It'll still interact into the 3D.
Yeah.
Okay.
So it seems like in our world, this is how things are, but it's not saying that there are extra dimensions. It's just if they are, they have to be smaller than some scale.
Interesting.
And there's also other like constraints you can place on these things.
Okay.
Yeah. This is also not my area of
Yeah, of course.
expertise.
Of course. And do we know how many, what's like the theoretical limit to these extra dimensions?
No, well, yes, people know. I don't know off the top of my head. But I think it's still, they're talking about it on very small scales, like sub-micron for sure, I think.
What is that
Like
measurement?
1 micrometer is like 1/1000th of a millimeter.
Okay, so 10
million
to the minus 6.
Yeah, a million times smaller than a meter.
Okay.
Yeah, exactly.
And that's where the extra dimensions might lie.
No, it's just saying that this is like currently, I think, the limit, but it might be way smaller than that.
Okay.
So of the size scale of the extra dimensions. It's not where they might lie, but it's like how, It also changes a lot about other physics. So, if you have gravity, for example, being this kind of not fictitious, but like not a real force in the sense of it's apparent as a force, but it's not really something that's an interaction. If you have extra spatial dimensions, it changes how gravity would behave on those scales. So I think there are people out there in the world who are trying to measure gravity at very short distance scales and try to search for these things. I'm not one of those people.
No, you're not. And so there's this other thing that you talk about, which is I'm probably going to butcher this, and feel free to correct me, is the isotropic 1 over r squared, and that's how we know we're living in the third dimension. Could you go a bit more deeply on that? Because I found that to be very, very fascinating, that there's like a direct proof of three dimensions.
It's not a direct proof. It's just like, so logically, if you work out like, you have something that's being emitted isotropically. So just for context, isotropic just means everywhere equally. So if I have a point in space and it emits like a something hot and it's very, very small, it would emit light, in this case infrared photons, isotropically in a sphere, right? So if you imagine the sphere and you have a little sensor somewhere on the sphere, the number of photons hitting your sensor would change depending on if you're really close or very far, just because of the effects of like things spreading out, right? So you can imagine this as like, what is the surface area of the sphere? It's 4 pi r squared. So forget the 4 pi, it's just a constant factor.
Right.
You have this r squared term. If we move further and further back, that means as a function of the radius, the distance from the source, you drop off in intensity as 1 over r squared. Okay, so as I'm really close to the source, more photons are hitting my sensor and my eyes in this case. As I'm really far away, less photons are hitting my eyes. And that scaling factor would be r squared, or 1 over r squared. This is the inverse square law.
Oh, yeah.
The reason it's related to this three-dimensional thing, the fact that we live in 3D space, is because you can imagine a sphere in 3D has this surface area of 4 pi r squared. But if you add extra dimensions, the surface area of some geometric object like that is getting larger, doesn't scale as r squared anymore. So that's how we know, like on a kind of everyday basis, that we have 3 spatial dimensions. That's not how we know. I mean, you can also just walk forwards, backwards, and jump up and down.
Right. But that's not a formula, right?
What do you mean it's not a formula?
Like walking forwards and backwards is not a formula.
Sure, yeah. But you can do measurements of intensity falling away as a function of distance.
Okay. So switching gears a little bit from the technical to more, I guess, broader questions about physics and, I guess, science as well.
Yeah.
I'm wondering, what are the limits of physics? And more specifically, like, where does physics differ from math and chemistry, per se?
What are the limits of physics? I have no idea.
In terms of, like, sorry, let me improve the question a little bit. In terms of, like, you would use physics formulas to calculate whatever you want to observe in the universe. But you wouldn't do that for chemistry all the way down necessarily, or biology all the way down necessarily. So, like, when do you need to switch, I guess, frameworks to go from physics to chemistry or physics to math, etc.?
I think that's a great question. I don't know if I have the answer to that in a satisfactory way, but of course you do have to switch frameworks because of just like computationally things become very, very hard very quickly. So in physics, like at least in my field, in subatomic physics, we talk about like very small particles. There's a handful of them, and we can calculate how they interact with each other. But then as we go into the level of like, okay, how do these particles deposit energy in our detector? We can't use subatomic physics to figure that out. We can't use like the standard model to figure that out. What we use is chemistry, and like you just look at like on aggregate like ionization, how does that work? So that is switching frameworks. And then your question about like math and physics, I think the main difference is like, well, in mathematics, you have a system, a logical structure that's built, and you just continuously build upon it. But there's no bound with the physical world. There's no like nothing, like as long as it's logically sound, that's mathematics, and you just develop it that way. With physics, it's like, no, it's not just logically sound, it also has to match empirical observations. And then with chemistry, it's the same thing. It's just like you said, it's switching frameworks. It's starting to look at things on a more aggregate scale, I think. But you should ask a chemist that. I wonder what Nico thinks about this.
I've asked him this question before. I think it was more about like difference between chemistry and biology.
Right.
But I'd have to go back with him on it. But chemistry and physics are kind of similar in the sense that they're very mathematically demanding, and they can also study at very fundamental levels. So what is is there like a clear border between the two fields, or do they overlap consistently?
No, but there's certain things in physics that have nothing to do with chemistry. For example, people talk about like general relativity and this idea of space-time. That's nothing to do with chemistry. But you also talk about like, the hydrogen atom. Like hydrogen atoms and modeling them in physics. Is that physics or is that chemistry? It depends on which like perspective you're looking at it, right? It's just two sides of the same coin. Essentially, we're still studying the hydrogen atom, or we're still studying, the next molecule you can think of, whatever. And sure, you can use things like the Schrödinger equation to solve for the orbitals of these electrons, but do you do it from a chemistry perspective or from a physics perspective? I think that's it. It doesn't matter. I think people can argue either way, and people have done it from both sides, and that's fine. It's just at the end of the day, we're trying to learn about the world.
Right. I think that also kind of goes into the lumping and splitting issues in science, where whether you should lump some things together or split some things together. So
I mean, I think cross-disciplinary learning is important just in general. So I think it's I think that's all I have to say about this.
Okay, no worries, no worries. How can physics in PopSci be more representative of what physicists actually do? I actually think this is a more important question than for other fields, because physics has managed to become a field of science that can be readily accessible in the popular culture, whereas other fields such as like linguistics is like nowhere to be found near and is popular. So, but there's also some I guess deception about physics, where if you just translate the formulas into a lot of words, it sounds very simple, but in reality, physics is extremely complicated.
Yeah. I mean, okay, so going back to your original question, like, what in pop culture isn't represented, I guess?
Mm-hmm. Or can it be more representative of what they actually do?
Well, okay, what we actually do as physicists varies, number one, a lot by, like, field in physics, but also there's a lot of, like, learning from each other. There's a lot of these types of discussions that happen. There's a lot of collaboration. It's very, like, not sort of a lone genius world anymore. I would imagine that I think maybe think tanks, like how they're represented in the media, are more like what physics departments are. But I don't know if that's probably the same for most STEM departments. Yeah, I think going to conferences is really interesting, and we never see that in the media.
Right.
At least I don't really watch physics shows, so I'm not sure. But yeah, I would say the main thing is just it's way more collaborative than people realize.
Okay. And this is also another question that I've been kind of holding for a while is, what is, academically speaking or theoretically speaking, what is like the end game of physics?
I think the end game is to construct a framework in which you can understand everything, every physical process that we've seen. Whether or not that's possible is up in the air. I don't know if it's possible, and I wouldn't want to be recorded saying it was or not. Yeah, I think that's the end game. I think we try to get better and better models for how reality works, and we wonder if there's a framework in which we can unite kind of all physical processes.
And that would be commonly referred to as the theory of everything, or the grand unifying theory.
Well, a theory of everything. A grand unifying theory is kind of a subset of that.
Okay.
Where they were looking for, or at least the way I see it is, you're looking for the unification between electroweak theory and the strong force, essentially. So like merging the three forces.
That's grand unifying, right?
Yeah, that's
Okay.
the grand unifying theories. There are people talking about trying to merge, build frameworks to merging the three forces in the standard model. So there are four fundamental forces we know of. There's the three in the standard model, and then you have gravity, which is, like we said, from Einstein's perspective, is not actually a force in the sense of it's an apparent force. Yeah.
Okay. Okay. And is it mathematically possible to model everything physically? Like, assuming the theory of everything would mean that you can calculate, obviously I think you can correct me if you're wrong, you could calculate every particle in the universe with exact precision, right?
No, because that's like a theory of everything that is computationally like possible. I don't know if that's ever going to be the case. Just because what do you use as a computer to compute every particle's position independently? You need a computer that can handle that many bits of information.
Right.
That is the number of particles in the universe. So yeah, those are different things. I think it's all it's saying, like a theory of everything is really just like a theory where we can, or a mathematical framework. This is another way of looking at it. A mathematical framework that can somehow, on the lower energy scales, which is our everyday, they distill down to the laws we're familiar with. Like, for example, Newton's idea of gravity, 1/r² laws, things like that. They still are very valid models of the way the world works. It's just that once you get to some mass, or like you look for very particular deviations from those laws, that's when you realize you need something new, and that's when Einstein came about and was like, hey, how about we try this other way of looking at it, which is this geometric structure. in general relativity. But I think I'm just rambling now. But
It's
basically,
okay.
basically, what I guess what I'm trying to say is, a theory of everything, it just needs to be self-consistent and has the ability to explain different physical processes well. That's it.
Okay.
Yeah.
And actually, a thought came as I was listening, as you said that the collaborative aspect of physics is not well represented. I think actually Oppenheimer kind of
Yeah.
showcased that.
Yeah.
It's not very obvious in that, it's about collaboration, but it shows the sheer scale of it. So I guess it's starting to come to light these days.
Yeah. Absolutely.
And another question I have is about the different periods of time in physics. So how do people in different time periods interpret physics, and what would they be calculating? And in other words, like, how would they see the world around them and its causal mechanisms?
Right.
Because the frameworks that they have they did influence the concepts that they're working with, right?
Yeah. I mean, so yeah, there were paradigm shifts that happened. The big two are kind of like at the turn of the 1900s. Is you have the development of quantum mechanics and you have special and general relativity. Before that, people thought about things in terms of like absolute time. Like Newton's kind of idea was like time is absolute. When you have two masses, they kind of influence each other instantaneously over arbitrary distances, and didn't really have this idea of time as actually an active variable that can be played around with, until Einstein came about. So that's one paradigm shift. The other one was like saying, okay, if I have, like, classical objects are completely deterministic in their path. Sure, you can have chaotic systems that are complicated, but like, if I throw this pen, I know exactly where it's going to go and where it's going to land. And actually, I can move my hand there because it's so built into our intuition that we know how classical physics works. Quantum physics doesn't work that way, in the sense that if I throw a quantum particle up, the probability that it ends up here versus here, we can calculate a probability distribution for that, but we don't actually know where it will actually end up until we measure it. So that's another paradigm shifting moment, I think. So on the subatomic scales, like, a lot of everything is just probability distributions.
Okay. And it's kind of funny, we only spoke about quantum till now. What is quantum physics?
Quantum physics is a framework in which you can calculate dynamics for systems which obey the axioms of quantum mechanics, I guess. Like, yeah. So there's this thing called the wave function. The square of that amplitude of the wave function gives you the probability of a particle being at a place at a given time. There are certain things you can't measure to arbitrary precision at the same time.
Arbitrary precision?
Yeah,
What does
so
that
like
mean?
this is like the Heisenberg uncertainty principle is like, I can't measure the position of something and the momentum of that same thing to better than some number. And that number is related to this thing called the Planck's constant. And so there are other variables that are like this, that are conjugate variables of each other, where you can only know so much about an object before you reach a limit.
And I'm trying to frame this question. You said there's only so much you can know an object before you reach a limit. And what is this limit exactly?
So, I mean, the example, like, so the Heisenberg uncertainty is this delta x, delta p, must be greater than h bar over 2. So on this side, this is how much you know about its position. That delta is just like the magnitude of how much you know about its position. This is how much you know about its momentum, so how much it's moving, how fast it is.
For those listening, the delta x
is your position uncertainty.
And delta p
is your momentum uncertainty. And then you have this h bar over here, which is just some number. So you know that this product of position and momentum uncertainties has to be larger than this number, h bar divided by 2.
Okay.
So this is one example of like this is the Heisenberg uncertainty principle in position and momentum space. Yeah. And this is not the case in classical physics. Like, I throw a ball, I can exactly calculate where the ball will be and how fast it will be going as a function of its trajectory. That's okay. That's allowed. In quantum physics, you can't do that. Yeah.
Okay.
I guess that's it. Yeah.
Okay. And how is quantum physics / mechanics discovered? Because this seems out. Because if it's outside the if it's outside the realm of classical physics, how does one actually kind of prove that it is real, or how did they do it back then?
Yeah. So you're now you're asking about the history, which honestly I'm not sure I'm the best. Well, I don't know for sure, but I think my understanding is it was a very patchwork process where there were certain things that couldn't be explained, and then people had propositions, and then you could explain away some of those things, and blah blah blah. And there was this whole revolution of a bunch of people coming together as being like, what can you actually explain, right? So for example, you have something that is a hot object, right, and it emits a light. That's what glowing things, hot glowing things, look red. Hotter glowing things look white.
Mm-hmm.
Hotter than that, they go blue. So there's a transition in the wavelengths they emit. And there's this big moment in physics where people calculated what the spectrum of those wavelengths would look like. And if you try to use classical physics and don't quantize the light, you end up with a spectrum that diverges as you approach the ultraviolet. So as you go to shorter and shorter wavelengths, the number of photons you'd expect to emit shoots up. And this problem was called the UV catastrophe.
Catastrophe.
Yeah, because we couldn't explain why this behavior occurred, but we didn't see it happen in nature.
Right.
So one way you can solve this is if you say, okay, but I can only emit discrete packets of energy, and we call those packets photons, in this case, so particles of light, and you recalculate the spectrum based off that, you end up with something that looks like this, which is the actual, the black body spectrum. So if you have an ideal thing that is glowing, its wavelength spectrum looks like this for a given temperature. And that's one side of it. The other side is you did particular experiments that showed that light is quantized, which is one of the experiments is called the photoelectric effect, which you shine light on a metal, and then you extract electrons from that metal, and it turns out that it doesn't depend on how bright your light source is, which is what you would expect if you thought of light as a wave, because the amplitude of that wave would be the corresponding to its energy. It mattered though what the wavelength of the light that you were shooting on the metal was. So short wavelengths, high energy. Higher energy kicked off electrons with more energy. But if I had a brighter source, I kicked off more electrons, but they would be at the same energy. So this showed us that photons themselves were quantized pieces of light. So they could have any arbitrary energy, but they come in packets. That was another thing. The other thing is if you look at atomic spectra, so you have a neon light, for example, you know that there are particular emission lines. And so Bohr started thinking about the Bohr model of the atom is you have this nucleus and you have these shells of electrons, and when electrons transition between the shells, that's when you emit light of a specific frequency. And those are colors that you see in chemistry. So there's many different things, and I'm probably missing a bunch of stuff, but there's many different kind of things that came about slowly over the early 1900s that led to the formulation of the standard formulation of quantum mechanics, which we now use daily.
That was such a cool explanation.
Yeah, I
appreciate
hope I
it.
didn't screw it up for viewers.
Okay, so what's next for you after you defend in 2-3 weeks?
Yeah, I hope to continue staying in physics for a while, at least for the next few years of my life. I still find it to be one of the most interesting things that I could be doing with my time. I really like the freedom and flexibility of what I can work on. And Honestly, I'll just keep doing it until it gets boring.
Okay.
And if I find something more interesting, then maybe I'll leave.
Okay. But in terms of like career trajectories, like where are you off to next?
I have no idea.
Okay.
Yeah.
All right. Well, Soud, thank you very much for this conversation. It was very tough, but it was
Yeah.
definitely learned a lot, and wish you the best of luck at Stanford.
Thank you. Yeah. Thanks.
Thank you for listening to this episode. To support this podcast, please subscribe to my YouTube channel, rate it 5 stars on Spotify and Apple Podcasts. I'll catch you at the next episode.